Two teams, one intense interval session. Afterward, the coach announces, Group A, ice bath. Group B, regular shower. Many athletes swear by ice baths for faster recovery. But do they actually work? To find out, you have to run a real experiment. A good experiment starts with a question. Here this question could be, does an ice bath actually help with recovery after training? To test that, you need two groups, a control group that does everything as usual, and a treatment group that receives the treatment. In this case, the ice bath. Only by comparing control group versus treatment group can you see if the treatment has a causal effect. And crucially, the assignment to groups must be random. Without random assignment, other differences between the groups could explain the results, and you couldn't draw a clear conclusion. So, what makes the treatment group special? The treatment group receives something new. That could be a medication, a diet plan, or, in our case, something as simple as an ice bath. The control group is the comparison or baseline group. They continue with the usual routine. Without a control group and random assignment, you have no reliable benchmark and no way to know if the treatment truly causes the observed effect. So how do you know if the ice bath makes a difference in recovery? Here's the challenge. Often, we cannot measure the thing we are truly interested in directly. In this case, recovery is a concept, a construct. We must decide which dependent variable measures it best. This process is called operationalization. The quality of your operationalization is critical for the experiment's internal validity. The better your measurement matches the construct, the more meaningful your results will be. Without a clear and well-matched measure, even the best designed experiment can give misleading results. If the players in the treatment group recover faster and the ice bath is the only difference, then chances are that the treatment is the actual difference. That's what scientists call a causal relationship. The difference can be traced back to the treatment, not to coincidence or external factors. Let's say after 24 hours, the data shows. The control group reports 60% muscle soreness, the treatment group only 35%. A statistical test tells you whether this difference is likely due to the treatment or if it could just be random variation. If the result is statistically significant, you found evidence for a causal effect of the ice bath on recovery speed. That's not just a feeling, that's a result. And that's what experiments are made for. The treatment group is the part of the experiment where something changes. Only by comparing it to the control group and ensuring random assignment can you answer, does it help or not? Science may begin with an idea, but it has to end with evidence. Without a clearly defined treatment group, without a control group, and without random assignment, you're left with a guess. Only together do they provide real proof. This principle also drives good business decisions. For example, a store chain wants to test a new pricing model. Instead of changing all stores at once, they randomly select half of their stores across the country to use the new prices, while the other half keep the old ones. If profits increase in the test group and pricing is the only difference, you can be confident about the cause. That's the power of random assignment, turning guesswork into real evidence.